Let's do an independent samples test. So this is right out of the practice test problems. So this is a group of 50 New York psychology students. Got a mean score of 530 on the psychology GRE with a standard deviation of 80. These students claim to be way more nerdy than a group of 50 California psychology students who had a mean score of 515 with a standard deviation of 50. Assuming the two groups were randomly selected, are the New York students truly more nerdy than the California students? You know, assume alpha 0.05 and using all 7 steps. Okay, so let's talk about what we know. So we know there's, again, so here's like there's a New York sample and there's an LA sample. Okay. We know that they have a mean equal to 530. They have a mean equal to 515. Right? Their n equals 50, and their n equals 50. That's nice. Their standard deviation for New York was 80. And standard deviation over here for California was, so they're not sigma, their S is 50. Okay, so they have a larger standard deviation than they do. Okay. So that's what we know. This idea that's talking about sort of way more nerdy, and again, truly more nerdy is giving us a directional test, and I'm assuming that the nerdiness is that they got a higher score on the Psych GRE. So really, we're testing out whether or not New York did better, was better at, or had a higher score than the LA sample. So it looks like because of more, we're dealing with a one-tailed test. So these are two different samples. They're randomly selected. They're independent. So we can't subtract their scores. That kind of stuff doesn't make any sense. So we have to do this as an independent samples test. All right. So let's start off doing the 7 steps. Step 1, step 2. So for my alternative, I really want to know if the mean mu for New York is greater than the mu for LA. It's pretty straightforward. I'm testing to see if this is true. For my null, it's just the opposite. Either New York and LA are equal, or LA did better, which in this case is not likely. I mean, we know the scores there, but we're testing to see if either, this is supposed to be done like before you collect data, that New York is either less than LA, or that the two groups are equal, both of which would make us believe that this alternative is not true. Okay. So for 3, again, it gives us that alpha equals 0.05, so that's pretty straightforward. For 4, we got 2 independent groups. They're from two different sides of the country, so we can assume they're independent and all that stuff. So we're talking about an independent samples T. Independent samples t-test. Step 5, we need to figure out our t critical with. Now again, remember whenever it's independent samples, our degrees of freedom for this is going to be n1 plus n2 minus 2. So we have 50 here, 50 there. That's 100 minus 2. So we're talking about a 50 plus 50 minus 2 equals 98 degrees of freedom. It still needs to be, one-tailed, and alpha needs to be 0.05, right? So we need to find a critical value for that. So I got to go with my t-table. So on the t-table, still want one tailed 0.05. Now I've got to scroll down and see if I have anything remotely that looks like 98. And I don't. Okay, so my choices are 95 and 100. If you look, the differences are not a whole lot, right? I mean, it's 1.6611, 1.6602. So it's going to be closer to the 1.6602, but just for sake of argument, let's grab the critical value for the closest degrees of freedom that doesn't go over. All right, so we're going to do it for 95. Let's make sure I'm in the right column again. 0.05, one-tailed, and go down to here to the closest without going over is 95. So I'm going to borrow this incorrect, but it's the closest I got without going over. 1.6611 is the closest. So let's go there. So this is not going to be equal to, but it's going to be something close to. All right, this is going to be close to 1.6611. It's not exact, it's not perfect, but it's close, because really here I ended up using 95 in place of 98 because 98 isn't on the table. All right. So that being said, my decision rule is, again, so think about it. I definitely am, I'm going, it's one direction. I'm looking for things in a positive direction. So I want everything to be in this side of the distribution. All right, so I want it positive. So my critical value that I'm finding here is supposed to be positive. So I want if my t observed is greater than 1.6611, I'm going to reject the null. That's my decision rule. All right, awesome. Step 6, if you remember, for independent samples, a little more involved than the step 6 for previous examples. So I need to think about 6a, which is to find the pooled variance. All right, so 6a is pooled variance. And it just happens that because our n's are equal, that this is the sort of easier case. When n's are equal, I can simply just add the two variances together and divide by 2. And I'll show you doing this shortcut and not doing the shortcut and show you this, you get the same answer if the n's are equal. But just here's the shortcut. I can take I have the s's, the standard deviations, right? I have those. So if I square the variance for 1 plus the variance for 2, divide by 2, it'll give me my pooled variance. So what is that equal to? Well, I need to square 80 because it's not a variance. I need to square 50, add them together and divide by 2. All right. So if I take 80 squared plus 50 squared, I get the top of this ends up being, 8,900 divided by 2 gives me 4,450 is my pooled variance. All right. 4,450 is my pooled variance. Makes sense, because 80 squared is about 6,400 would be the variance for New York. 50 squared is about 2,500, which is the variance for LA. Yeah, you average those out, you get 4,450. The other way that you could do this, the other way that it could be done, is if you hadn't noticed that the n's were equal. I'm going to erase this for a second just so I have some room. If you hadn't noticed that the ends were equal and you decided to do the weighted average thing, the good part is you'll get the same answer. Right? The answer will be exactly the same as it is here. It's going to take you slightly more work. Okay, so here's another version of the pool variance. S squared, put the P on top instead of on bottom. S squared P equals to, I need N1 minus 1 times the variance of group 1 plus N2 minus 1 times the variance of group 2 over N1 plus N2 minus 2. Awesome. They're both the same size. They're both 50, right? So that means I'm going to have 50 minus 1 times 80 squared here plus 50 minus 1 times 50 squared there over 50 plus 50 minus 2. All right. So let's figure that out. 49 times 80 squared equals some massive number. 313,600 is everything here, okay? Plus, I need to take 49 times 50 squared, which is 122,500 divided by 98, because that's 50 plus 50 minus 2. All right, so 313,600 plus 122,500 equals 436,100 divided by 98. So 436,100 divided by 98 equals 445. Which is the same thing as here. Right? So if I did it either way, I get the same answer. Just this way is a lot faster. So if the ends are equal, this is sort of I can do. I'm trying to think. I can do this. I'm trying to write this. I can do this approach because N1 equals N2. That's what makes it easy to then just pull them together. The idea there is because the weights don't matter. I don't need to weight one group more than the other because they both have the same n. So they're both equally weighted. So I can just forget all that stuff and just really just take an average. All right, so let's get to 6b. 6b is I need to then use this number to figure out the standard error of the differences between the two means, which is the square root of the pooled variance over N1 plus the pooled variance over N2. So I just need to plug this number in here. So that means the standard error of the difference between the two means equals to that 450 over 50 plus 450 over 50 square root. All right, so let's figure that out. So knowing that they're the same, 450 divided by 50 equals 89. I see that twice, so times 2. So 178. Inside this is 178. I can take then the square root of it and get that this equals to 13.342. Let me make sure I did that right. 4450 divided by 50 equals 89. 89 times 2 is 178. The square root of 178 is 13.342. So that is my standard error, the differences between these two means. And that's my standard error. All right. So now we need to go to step 6C, which is the final step 6. Now you just plug this into t observed. So here's 6c is I need my t observed. I'm just going to plug this number in there. So I need the two different means, which were 530 and 515. Okay, so it's going to be, I'll just write it generically here first. So m1 minus m2 over the standard error of m1 minus m2. All right, so this is my 6c. So I'm going to draw a line down there again. So my t observed equals 530 minus 515 over, we figured this out already, 13.342. All right, so 530 minus 515 is 15. 15 divided by 13.342 equals 1.124. So we can then go to our step 7 and say, well, since 1.124 is less than our 1.6611, do not reject the null hypothesis. All right, do not. Our t observed was not larger than 1.6611. We said, look, if t observed is greater than this number, we're going to reject. Well, it's not. It ended up being smaller than that number, so we're not going to reject the null hypothesis. So this is evidence that there's likely no difference, even though the New York students scored 530 and the California students scored 515. This is not enough evidence to prove that there is a significant difference between those two numbers. Meaning that if we were to do this again, take different samples of New York and California students, New York and LA students, you would likely get different similar numbers. It's too close together, even though it's 15 units. It seems like a lot. They're really too close together because the standard error is like 13 units. They're really too close together to really say that there's a significant difference, even though the New York students scored higher. So in this particular case, we do not reject the null hypothesis. There is not evidence that New York is smarter or they scored higher, significantly higher on the psychology GRE. Anyway, so that's an independent samples test. So we went through all the 5 steps. We did these 3 steps of step 16, step 6, 6A, 6B, 6C, to find the t observed. Really, it's just pooled variance. Use the pooled variance to calculate standard error, and then do your t observed, which is the typical step 6. And then compare your t observed to your t critical and make a decision about whether or not you're rejecting or not rejecting, what sometimes we call retaining the null hypothesis. And that's it. It's a little bit extra work because you got to find the pooled variance in order to find the standard error. But other than that, it's a very similar process to the one sample dependent samples. We're just doing, we're just finding a t observed where it's some difference over a standard error. It's just this standard error is a little trickier to find than it is for a one sample dependent samples. Anyway, so there's examples of some probability, examples of one sample tests, example of dependent samples test, and example of independent samples test that you'll see on an exam or in your practice problems or on your quizzes. So hopefully this will help make this clearer. And of course, if you have any questions, feel free to email me or come by during office hours and talk to me. And that's it.